Hi again. This video is going to look at a common type of exam question and a common question in general that looks at the combination of two equations, W equals QV, that we should have just watched on the video above, and E equals a half mv squared, which is the kinetic energy equation which you will do with Sandy and you should remember from GCSE. So what we can see is combining these two equations, we can see that work done on an object, the energy given to an object, must be equal to the energy that it has. In certain cases that is all kinetic energy, and we're going to assume that in this case we've done a lot of work to an object and it's all turned into kinetic energy. It's all been transformed into kinetic energy. So a situation that might be the situation I'm going to describe below, which is an electron being accelerated through a potential difference. What we need to do to start that is know that we can combine equations like this when we assume something like work done equals kinetic energy. I should put a little subscript K there. So we're going to assume all the work that we do on this electron turns into kinetic energy. From that we can say that QV, or in this case EV, because we're going to deal with an electron, the charge of an electron times the potential difference, EV, is equal to the kinetic energy, which is combining these two equations. So that's the first thing. Make a note of that, write that down somewhere. So this is our question. If an electron is accelerated through a potential difference of 1000 volts, how fast will it be travelling by the end of this process? Assuming that it started from rest, that the initial speed or velocity was 0. Right, so this is what it looks like. We've got some sort of cathode over here. We call it a thermionic cathode, where it's emitting electrons by getting the surface really hot and then flying off of the surface of it. As soon as they're off, they're under a potential difference towards a cathode, from a cathode towards an anode, and that potential difference is 1000 volts. So they've been very attracted to the other side. That's going to speed them up. What do we know? This is what I like to do with exam questions. I always like to write, what do I know? Because I need to think, what terms can I shove into here? And often, you might need to know something else as well that you might not have thought about. But this is not that case. This is a simple case of filling in equation gaps. So what we know is, we know the charge on an electron. It's the fundamental charge, it's the elementary charge, and it's 1.6 times 10 to the minus 19 coulombs. We know that one. We also know the potential difference. It's 1 kilovolt, or 1000 volts. So we know that one as well. And we also know the mass of an electron, 9.11 times 10 to the minus 31 kilograms, which is incredibly small. Both E and N, the fundamental charge, and the mass of an electron will be provided to you in formula books. So you don't need to memorize them, but you probably will end up remembering by the end of the course. So we have all three bits of information that are missing from our equation, except for V, which is what we're trying to solve for. So what I'd like you to do now is pause the video and see if you, with this information, can solve for V. Please try. Right, so we're back. What you should have done is you should have attempted it, and hopefully you've got it correct. So what we're going to do is we're going to just go through it now. I've got what we know over here, E, M and V, which we just said, and I've got my equation here, EV equals a half mv squared. So all we have to do is be able to rearrange this equation to make velocity the subject. So we can see we're just going to take half m in front and bring it underneath EV, and then we'll square root. Now divided by half is the same as timesing by 2, so I've just put the 2 up there. So we end up with the square root of 2EV over m is equal to our velocity. Go and be careful when you're using V's and V's. So we need V for voltage, or potential difference, is a large V. V for velocity, I usually use a small v with a little flick. So, square root of 2e big V over m is equal to little b. So, we stick our numbers into that equation now, and what we've got to be very careful of here is, on our calculators, that we don't make a slip up. Because it's very easy when shoving huge numbers with huge powers, usually negative powers as well, especially with negative powers on the bottom, mistakes get made with all the messing around on our calculators. Practice that and then you will avoid making those mistakes in future. We should have got the answer of 1874, 1994 0.27. I would ask you, do you think that that's a correct answer? And obviously that's a weighted question, isn't it? Because why would I be asking it? The fact is, it's to a ridiculously high precision. Far too many significant figures in that. I've only ever given you 4 significant figures. At the worst, only 2 significant figures. So 3 significant figures would be sufficient for this. So this level of precision is totally unwarranted, and not only unwarranted, but totally unjustified as well. So we need to get rid of a lot of these significant figures. So I'm going to go to 3 significant figures, and so I'm going to take it and change it into 1.87. Now I'm not rounding the 7 because there's a 4 there. So 1.87 times 10 to the, well, how many powers is it? 1, 2, 3, 4, 5, 6 times 10 to the 6 meters per second. Now that's in 3 significant figures, and it's totally justified because of the information that we've put in. This is in too many significant figures. For example, if I change that to 1.61, it would change that number a lot, and we don't know whether it is 1.61 or not, because we just haven't said. We haven't put 1.60, so we don't know that it's not 1.61. I hope that's clear. Anyway, so, did you do it? Could you work it out? I hope so.